Hi, everyone. I hope you all had a good and restful winter break, and welcome back to Talk Math with Your Friends, the spring season. It is my pleasure to introduce our first speaker, Dr. Joshua Bowman of Pepperdine University, and he studies geometry and dynamics, and today he will be telling us about Chebyshev polynomials. So please join me in welcoming Dr. Bowman.
Thank you so much. All right, so in the spirit of being interactive, and just Brian mentioned his level of familiarity with Chebyshev polynomials. Let's go ahead and start out. Chebyshev polynomials are well known, I guess, in certain circles, but not all, and they're known for different reasons. So just so I get a sense, would people put in the chat what Chebyshev polynomials make you think of? And if you don't, and they don't make you think of anything, you can say, yeah, I just don't know what they are. So I'm curious what kinds of things. Hopefully there'll be some new things to everybody. But I'll be just giving my perspective on them.
I think of Star Trek.
Awesome.
Okay, I see interpolation, numerical analysis. I think I saw somebody maybe mention orthogonal polynomials. I see Chevy Chase. Okay, all right, great. So so hopefully this will be fun. I do not do numerical analysis. I do dynamics. So we'll get so this will certainly be a different perspective, I think, than most people have seen before. So I want to start out just by talking about where these come from. These are one of these unusual objects that are actually named after the person that introduced them. So Chebyshev, in the 1850s, he was very interested in applications of mathematics. And so he wrote this paper on the theory of mechanisms known as parallelograms. So he's building on work that was done by Watt a few decades earlier. And basically the problem he's trying to solve is, how do you convert motion from one kind to another? So you've seen these gadgets that take a circle and somehow turn it into something that moves in a straight line. Okay, and so this is something that's at the time needed for steam engines and things like this. And Chebyshev came up with all sorts of great gadgets, which I'm not an expert on, but there's cool animations and things like that out there. So that was a practical problem he was looking at. This paper is kind of in two pieces, and then there's a mathematical problem, which is to find a polynomial of a given degree that minimizes the maximum difference. Okay, so minimize the maximum difference with some other function. And he was looking at an arbitrary interval, but then he rescaled it, so it's -1 to 1. So I'll just start with that. So you have some function and you want to fix the degree of a polynomial and find how you can minimize the maximum difference with that given function. And it kind of makes sense that I think to see that these might be related, right? So when you're doing this converting one kind of motion to another, you want something to follow a straight line, but you're doing it by some other kind of process. And so your mechanism is not going to follow a perfectly straight line. You want to minimize that difference with the motion you're trying to reproduce. So it does seem in principle that these two ideas are related. It's not clear that Chebyshev actually managed to do that. You get to the end of this paper and the last paragraph literally says, okay, in the following paragraphs, I'm going to explain how to apply this mathematical theory to this practical problem. And then he just stops. Like there are no following paragraphs. It's not clear that he managed to pull these together, and so we're going to focus on the mathematical side and not the mechanical side. But he did essentially solve this problem, or some simplified version of this problem. And the thing that I want to pull out is that he finds that the difference between the function you started with and the polynomial. Do y'all see my mouse, by the way?
Yes.
Okay,
yep.
So I can point things on the mouse. Great. So he finds that the difference then should be a multiple of this expression. Okay, and he does this through solving some differential equations and things like this. So now you look at this, I'm claiming that this is a polynomial. This might not look like a polynomial to everybody because there's this square root in here in these two places. But if you'll look, you'll see that there is the square root of z squared minus 1. There's a plus in one case and a minus in the other. And if you expand out using the binomial formula, you'll notice that the only time that you'll get a square root is when there's an odd power on that. And so in that case, the plus and the minus will cancel out. Okay, so this is the polynomial, and we'll see that in some other ways later. These are often labeled as T sub n. T here stands for Chebyshev. There's lots of different ways to transliterate Cyrillic into English, and so some of them start with T, and so T is very commonly used for this. Okay, so this is the expression that he comes up with, and now I'm going to forget all the origins of where this came from. We're just going to talk about these functions. Okay, and then there could be some higher order terms. Another way to think about these solve lots of different problems. That's part of why they show up in so many different ways. If you look at polynomials that map the interval from -1 to 1 to itself, then these functions will maximize the leading coefficient of those polynomials. Okay, so it solves that sort of maximization. And then if you divide out by that leading polynomial, then that leading coefficient, then you solve this minimization problem he was trying to solve. Okay, so that's where these come from. Now what I'm going to do for a little bit is play around with these, with this expression. So here's the formula he found, and I'm going to just substitute out so that I don't have to deal with these square roots as much anymore. So this thing inside here, the z plus root z squared minus 1, I'm going to call that t. And then there's this little trick that sometimes we use in calculus classes when we're trying to find limits or things like this, where we take the conjugate expression. If we change that plus out front of the square root to a minus sign, then that actually, in this case, is the reciprocal. So if t is z plus square root of z squared minus 1, then 1 over t is z minus square root of z squared minus 1. So a little bit of algebra that you can do there. And if you add those two together, you'll get 2z. And so what that means is you can say that z is 1/2 of t plus 1 over t. Okay, so now I'm going to forget about the square roots. Okay, so again, a little bit of algebraic trickery here to get these different expressions. And now using that, we can rewrite this defining equation. So going back up to the way that t sub n was defined, if you plug in, instead of z, you take this 1/2 t plus 1 over t, then so that's what's on the inside of the function, and on the outside, the result then just takes t to the nth power and 1 over t to the nth power, right? Because that's what we had up at the top. We had t to the n plus 1 over t to the n. Okay, so this is another way to think of that equation, is that t sub n sends 1/2 t plus 1 over t to 1/2 t to the n plus 1 over t to the n. Now you won't see it written this way very often. I'm allowing for t to be complex here. These square roots from earlier were branch cuts and things like this. We're trying to get away from worrying about all that. I'm allowing t to be complex, but in particular, if t is a unit complex number, then if you add that number to its reciprocal, you're going to get, you're just going to get the cosine of the argument of that. So if t is cosine theta plus I sine theta, then 1 over t is cosine theta minus I sine theta. And so this expression just becomes t sub n of cosine theta equals cosine n theta. So in some sense, this polynomial is taking some angle and just multiplying that angle by a factor of n. Okay, and this is the expression you'll more often see, is this one at the bottom here. Okay. All right, how are we doing so far? Any questions? I'm not following the chat right now, but are there any concerns right now?
Nothing stated.
Cool. All right. So I'm going to keep playing around with these because I want to get these into a little bit of a form where I can mess around with them a little bit later. I'm going to do a minor change of variables. So right now I have 1/2 t plus 1 over t inside the polynomial, 1/2 t to the n plus 1 over t to the n outside the polynomial, and that 1/2 in there, it bugs me. it's fine for some things, but I don't like using that, so I'm going to get rid of that 1/2. But that means that I pick up a factor of 2 in front of the cosine. So I'm just rescaling on the inside and the outside at the same time. Okay, and you don't have to worry about this because we're never going to see the cosines again, really. So this is now going to be my new definition, and it's just a rescaled version of the polynomials from before. Until I say differently, I think I've managed to keep this throughout the rest. Now z is going to be just t plus t inverse. Okay. So what we can do, and this is I think a cleaner way to see that we have some polynomials coming out of this. We can develop a recursive formula from this expression. So we have the t to the n plus 1 over t to the n. That's over on the left side of this expression. And on the right side, well, this looks maybe a bit mucky, but let's just think about multiplying it out. We have t times t to the n minus 1. That'll give us t to the n. T times 1 over t times 1 over t to the n minus 1 gives us 1 over 2 to the n. But then if we do the developing and we look at what the cross terms are, then we pick up an extra t to the n minus 2 and 1 over t to the n minus 2. So we're just going to subtract those off from this product, and that'll give us what's on the left. And so from this, we can actually get a recursive expression. I'm going to throw in t to the 0, t sub 0, which just sends everything to t to the 0 plus 1 over t to the 0. That's 2. T sub 1 is the identity function, but then there's this recurrence relation that tells us how to compute Chebyshev polynomials, knowing the earlier ones. Okay? And maybe this isn't too much of a surprise if you've seen different expressions for like Fibonacci numbers. You can write an explicit form for the Fibonacci numbers, which is similar to the one we had earlier that has some square roots in it. But you can also get a recursive formula, and so this is sort of similar to that. And just to highlight, in case you're having trouble seeing where these come from, the z in this recursive formula is that t plus 1 over t. Then the previous polynomial t sub n minus 1 is this bit in red, and t sub n minus 2 is this bit in green. Okay, so that's the recurrence.
I love the connection to Fibonacci, and it also reminded me a little of the first year's dream, where you could ignore the middle terms when you expand out a polynomial to a power, and then you just add it back in the correction terms. So you're like formalizing the first year's dream. Love it.
Yeah, yeah, and the correction terms just work out to be particularly nice in this case. Okay. So now with this rescaled version, so remember I took out the 1/2, so now instead of going from -1 to 1 in that interval to itself, now we go -2 to 2 in that interval to itself. And in this case, you can see that these are monic. So the leading coefficient is always 1. And you might want to work out what the next couple are. While you're doing that, I'm going to switch over to a different window. If I can remember how to do this. Okay, so this is a Desmos file that I've used to draw some of these polynomials, and I think that's going to show up in the chat if you're interested in looking at it and playing around with it yourself. So what I have here is that the first two, t sub 0 and t sub 1, are already drawn. And I haven't told you what the rest of them are. I've just written down the recursive formulas. We are going to come back and see T2 a little bit later, so you might want to work out what that is. It's probably not surprising that it's a quadratic. So we see that that blue parabola showing up. And I'm just drawing from -2 to 2, right? So I'm forgetting what happens outside of that. And there's the cubic one. And there's the 4th degree one. And the 5th degree one. And you get sort of these nice patterns coming from this. But we'll pause right here. Do you notice anything about these polynomials, about their graphs?
There's a lot of interesting shared points.
Mm-hmm.
See, they all cross at -1, local maximum minima are at 2 and -2. I probably have to.
Yeah, so the
There's some
the
odd
local
even-
maximum and two minus two are important for Chebyshev's original problem, right?
There's some odd and evenness going on here that I'm having trouble just keeping track of the colors to check on.
Yeah, so each time we go to one, we just increase the degree by one. So these are they're alternating. The degree of the polynomial is equal to its index. So maybe I'll do these one at a time, and I'll turn off the first degree one. So that's the second. That's the quadratic one, and there's the cubic one. There's the fourth degree one. So remember, one of the important things about these is they map the interval -2 to 2 to itself. Okay, so we're seeing people noticing the peaks, and where are the peaks? Yeah, what do you notice about the maxima and minima?
Are they derivatives of each other?
Not quite. If you look at derivatives, then you get a different set of Chebyshev polynomials. They're almost evenly spaced. They're evenly spaced with respect to this angle that we'll come back to. But do you notice that the maxima and minima are always the same? You don't like go up and then go down a little bit and then go back up, right? Everyone is always all the way out at the extremes, all the way from at -2 and 2. Okay, so all those extreme values are the same. Okay, and so that's going to bring us to some of the dynamical aspects of these polynomials, which is really what I want to talk about. Okay. All right, so this is these are polynomials, so they're smooth, but there's actually in secret a kind of folding that's happening here. So what you can describe going on is that you're taking an interval, stretching it out by a factor of n, okay, for the nth polynomial, then folding it back in on itself, and then just sending that back to the original interval, okay? And when you fold it, all of those pieces are in some sense the same length. Now they don't appear that way with these polynomials. So I want to explain where that comes from, and that's where I'm going to start using my trusty whiteboard back here, okay? So first, I want to think about what happens if you just take z and raise it to z to the n. Okay. So when you do this, and on the unit circle, so this is where z equals 1. On the unit circle, this is going to take every angle, right, and multiply that angle by a factor of n. Okay, so what that means is that this entire circle is going to wrap around itself, and it's going to do that n times. Okay, so each one of these little pieces is going to wrap around the entire circle. Okay, so that's what happens when you multiply an angle by a factor of n. Anything, if we go from 0 up to 2 pi over n, that will cover the entire circle. Okay. So now what happens when we take this and we map it to the interval from -2 to 2? Okay, so this is the map that takes t to t plus 1 over t. Okay, so two numbers that are inverses of each other go to the same point. Okay, so that means that any point on this unit circle, its inverse or its reciprocal is the point on the bottom, and so each point that's on the top and the bottom are going to go to the same point on the interval over here. Okay, so these two go to the end over there. 1 just goes to 2, -1 goes to -2. The 2 points here in the middle go to 0, and so forth. Okay, so this map from the circle to the interval just sort of collapses the top and the bottom parts of the circle. So now if we multiply by a factor of n, well, this interval is getting covered twice already, right? It's getting covered by the top of the circle and by the bottom of the circle. So if we raise to the nth power, we can think of breaking the top part into n pieces and the bottom part into n pieces. And we'll just focus on the top. And what we see is, well, this whole thing, this piece of this that was goes from 0 to 2 pi over n, that went around the entire circle. And so if we multiply that angle by n, the first chunk that goes up to just pi over n is going to go to the top half of the circle. And the next chunk is going to go to the bottom half of the circle. But both of those go to the same place on the interval. So we're going to go from here to this endpoint. That's going to be the first piece here. And then the next piece is going to go back. And so we're folding back and forth and back and forth as we go along these different segments. And so it's like we're just taking this segment, stretching it out, folding it, and then it goes back exactly where it is. Okay, so put that in words. So we thought about what happens on just this this regular power map on the unit circle, and then if we take the unit circle and squish it down onto the interval, then we get the going back and forth folding behavior. Okay. All right, so that's what happens on that interval. So that's part of the dynamics is this folding dynamics.
Can I ask a physical question? This might be way off topic, but is this, so you said there was like physical gadgets about changing motion. Should I be imagining this kind of like a piston going along the interval and turning into a rotating axle, like that level of physical motion change?
Yeah, so there's actually there's another way to describe it, because that motion won't always be exact if you're trying to think of it in terms of a piston. But if you think about starting with the circle that has this as a diameter, okay? So think about the big circle. I'll just stop sharing real quick. So think about the big circle that has this as a diameter, okay? And then if you have another circle of half the radius rolling around inside, right? So this is one of these roulettes, these hypocycloids. If you mark a point on that inner circle and watch as the inner circle rolls around the inside, that is just going to go back and forth on that diameter. And so basically what we're doing is we're speeding up the rate at which that inner circle is rolling.
Cool.
Okay. All right, so now let's expand the picture and think out besides what's just happening on that interval. So a few decades later in the 19-teens, Fatou and Julia started studying iteration of complex functions. Okay, so now we're looking at holomorphic functions, and so that maps the complex plane to itself. And for each point, we say, okay, where does that point go when I apply the function once, and then when I apply the function twice, and when I apply the function 3 times, and so on. And we get this sequence of points for each point in the plane. We get this, what we call the orbit of it, as we iterate the given function, okay? This is, I think dynamicists are the only one who do this, and so I want to make sure that I'm clear when I have this superscript here, it's not an exponent, it's a composition. Okay, so when I say f to the k, that's f composed of itself k times. Okay, and then the goal in this study is to classify what these orbits do. Okay, so can I predict what's going to happen for any given point, predict what's going to happen in the long term as I repeat this process. All right, so a little bit of warm up. This is the next interactive thing for everybody. So we're going to start with just the power map. Okay, so pick your favorite degree, raise n to that power, And what we're going to do is take a number, take any complex number, raise it to that power, raise it to that power again, and then keep going. Okay, and we want to predict what happens to that sequence. So first question, and we'll pause for a few seconds. I want to try this idea that I've seen, which is not everybody just type in their answer as soon as they think of it, but type in an answer and then wait, and we'll all put it in at the same time. Okay, so think about if you pick a number whose absolute value, whose modulus is less than 1, what do you think is going to happen to this orbit? Okay, and if you're not comfortable thinking about complex numbers, that's fine. You can just think about what happened if this were a real number. Okay, and we've raised it to the same power over and over again. All right, so take just a couple of moments, think about that. Enter it in the chat, but don't hit enter yet. All right, and 3, 2, 1, go. Let's see what we get. Okay, so I see goes to the origin, spirals to the origin. All right, so we seem to agree that because its modulus starts out less than 1, it's going to just keep getting smaller and smaller and go to 0. Okay. All right. What about if the modulus is greater than 1? What's going to happen? Type it in, but don't enter yet. Okay. 3, 2, 1. Let's go. Okay, spiraling outward, blowing up. All right, flies away. So in that case, it's going off to infinity, and we need to be precise about what we mean with that. Well, since we're working with complex numbers, it will do the usual thing and just say any direction you go gets you to the same point at infinity. So there's just one point at infinity, so we can think like we're acting on the Riemann sphere. Okay, so all these, if you start off outside the unit circle, you're going to go off to infinity. And then lastly, what if you start on the unit circle? All right, 3, 2, 1. What happens? Okay. So, all right, so stay on the unit circle, maybe fill it in, maybe be periodic. Yeah, okay, so there's definitely, so I think we agree that it'll stay on the unit circle. Whether it's periodic or whether it fills up the unit circle depends on some careful thinking about what that angle is. And it could be different, and there could be numbers that are very close, which are very different. And that's sort of a key feature, is this expansion that's happening on the unit circle is causing things to get really spread out, and even if they start out close, they may behave very differently in the long term. So that really is the fundamental dichotomy that we look at. So whenever you have a complex dynamical system, we tend to break up the space that we're acting on into these two pieces. We have what we call the Fatou set, and in the Fatou set, points that start out close together stay close together, and they behave the same way. And then on the Julia set, which is the complement of that, that's where the chaotic dynamics happen. So if you points start out close, they can end up behaving very differently in the long term. So in the case we just analyzed, if you're inside the unit circle, everything goes to 0. Okay, and that's an open set, so nearby points will also go to 0. If you're outside the unit circle, you're going to go off to infinity. But whereas if you're on the unit circle, well, first of all, there's things which are off the unit circle, so either going to 0 or infinity. So they started out close, but they're going somewhere else. But also, even on that unit circle itself, points that start out close, this expansion is forcing them apart. Okay. All right. So those are the two pieces we're going to look at, and we're going to look at that with some other systems, starting with these Chebyshev polynomials. Oh, yeah. So I did want to show this one other thing. So we're going to look at. Did I do this yet? Did I do this out in the wrong order? I think the order I sent to the organizers is not quite what I intended to, but that's fine. We're going to switch over.
So now you have 3 copies of the same link.
Okay. There's a lot you could do with this. I just want to highlight a couple of things here. So Fatou and Julia did not know about the Mandelbrot set. Of course, it didn't start getting studied until like the 70s. But Julia actually had a pretty good handle on what could happen, what the type of the Julia set could look like, even if you didn't really have a good sense of all the different rich possibilities that we've seen. But I would just want to highlight a couple of special cases. So what I put my cursor right at or pretty close to the origin. So this is now just for the polynomial z squared, okay? And you see that there's the circle, that's the Julia set, and then the inside and the outside make up the Fatou set, okay? So there's this nice simple Julia set. And then as you move around here, you get all these different shapes, okay? You move into different pieces. I am just gonna go, because I don't know how many people, even if you've thought about the Mandelbrot set at all, have thought about what happens when you go all the way out here to the end. All right, so that far leftmost tip is at -2. So this is for the polynomial z squared -2. And if you worked out the recursive formula earlier and held on to that quadratic expression, then you would have seen that that's the quadratic Chebyshev polynomial. Okay, and here I can't move my mouse to show you, but you can see in the Julia set picture, it's just that segment. Okay, so everything else is the Fatou set. Okay, so this is, so it's another special case like that. All right. I'm not going to go back to my slides. I actually want to go ahead and share the next Desmos screen with you. Okay, so let's think about how we can take what we now already understand about the power function and transfer that over to information about the Chebyshev polynomials. I've drawn here a bunch of different circles. The red one is the unit circle. And then there's circles of radius 2, 4, and 8 in green, circles of radius 1/2, 1/4, and 1/8 in blue. And what I'm going to do is slowly transform this. I'm going to add, so thinking of these as complex numbers, I'm going to add to each number z a multiple of 1 over z until I get up to the function z plus 1 over z, or t plus 1 over t that we're looking at before. And you can see that the circles that started out inside the unit circle are getting pushed outward, okay? And then they're joining up with the circles that were on the outside. The red circle, the unit circle, I'll go ahead and stop this when it gets to the end. That unit circle is in fact collapsing down to the segment from -2 to 2, okay? And then every circle on the inside of the unit disk is paired with a circle on the outside, and that gets transformed into an ellipse. Okay, so all the other circles around the origin are transformed into these ellipses.
Are the -2 and 2, are those the foci of the ellipses?
I hadn't thought about that. That might make sense, wouldn't it? I'll have to think about that. It's a good question. Okay, so we look at what happens with these circles. The circle of radius r, think of that as being outside the unit circle. The circle of radius 1 over r go to the same ellipse, and its major axis is 1 plus 1 over r, and its minor axis is r minus 1 over r. If r was greater than 1, then you don't need the absolute values here, okay? All right, here's another way to write that equation that I used for the Chebyshev polynomials earlier. So we're going to take P to be the power map. Psi is the t plus 1 over t. Psi here, you can think of it as being like the cosine, if you like. Maybe it's twice the cosine. But this equation, we can think of this equation as defined this way: t sub n composed with psi is equal to psi composed with p sub n. And so this is essentially how we're transferring our understanding of the power maps to the Chebyshev polynomials. I see somebody saying, I'm imagining this on the Riemann sphere and it's uncomfortable. It is actually a really neat thing if you want to think about this on the Riemann sphere. This is actually it's just the squaring map, except you've moved where the critical points of the squaring map are. So if you understand the squaring map on the Riemann sphere, we just sort of rotated 0 and infinity so that they go to different places. And so it actually can be useful to think of it as happening on the Riemann sphere. Might be better to put the 1/2 factor back in there so that 1 and -1 go to themselves, and those are the critical points, and everything's sort of wrapping around that. All right, now what we know about the power map is that it raises the absolute value to the same power, and so circles of radius r get mapped to radius r to the n. Okay, so when we take that and we transfer it over to the Chebyshev polynomials, we had the unit circle, which gets mapped to the segment. That segment is staying fixed. It has this folding dynamics that we've seen, right? Then off of that, you have these ellipses, which came from the circles before we applied psi. And so we have these ellipses, and each of those is going to get mapped out to another ellipse corresponding to taking the nth power of the modulus, and it's going to wrap around that outer ellipse n times. Okay, so the segment folds, all the other ellipses, they map out to bigger and bigger ellipses, wrapping around more and more until everything goes off to infinity. Okay, and so that's what's happening on we have the folding dynamics on the segment, and then this very well-controlled dynamics going off to infinity on the ellipses. Okay, so now we can classify the behaviors. On the segment, they have the folding dynamics, and off the segment, they tend to infinity. Right, so that's the Julian-Fatu set for these one-dimensional Chebyshev variables. All right, are we ready to go to 2 dimensions?
Yeah, let's do it.
Okay, so I've tried to set this up so a lot of stuff is analogous, and it will. I'm gonna. Yeah, I'll say it real quick. So another nice property of Chebyshev polynomials is if you take 2 Chebyshev polynomials and do them in either order, the result is the same. So they commute in that sense. And the same thing is true for power maps. And one thing that Fatu and Julia proved is that those are the only 2 possibilities. If you have 2 polynomials that commute, then either they're both up to some conjugacy, both power functions, or they're both Chebyshev polynomials. So that's another nice property, and I only want to mention it because it was one of the inspirations for this generalization. So in the 1980s, Alexander Veselov and then Hoffman and Withers, working together, both produced these generalizations of Chebyshev polynomials to all dimensions, and in lots of different ways. I'm just going to describe one way to do that. Veselov did it in terms of Lie algebras, and Hoffman and Withers expressed it in terms of root systems and affine Weyl groups. If you're familiar with either of those, you know that they're related to each other. So these constructions were essentially equivalent, but they were motivated by different things. Veselov was motivated by this question of what things commute and what things commute in higher dimensions. And Hoffman and Withers were really interested in this folding dynamics. Okay, so here's how the generalization works in one case. So in 2 dimensions, now I'm going to have 2 values of t sub 1 and t sub 2, and 2 values of z sub 1 and z sub 2. And before I just sent t to t plus 1 over t. Now I'm going to take t1 and t2, send it to t1 plus t2 plus 1 over t1 times t2. And then the reciprocals of all of those. So 1 over t1 plus 1 over t2 plus t1 t2. Okay. So hopefully you see this is sort of analogous to that little psi function from earlier. I'm using a capital psi now to indicate this map. All right. The power map I'm going to use, I'm just going to take the nth power in each variable separately for the t's. Hi. So
Yes, come.
you want to come in and say hi? Okay. This is my daughter. You want to have a few jelly beans? Mama has them in her office.
I have the jelly beans out here. Okay, we're okay.
Okay. A question about whether there should be any stray 2s in here. It would actually be a stray 3 in this case because there's 3 terms. But the normalization I've used manages to get rid of all that, so I can keep the coefficients the way I have them here. All right, so my power map is just the nth power map in each component, and I'm going to use the same expression from earlier. T sub n composed with psi equals psi composed with p sub n. That gives me a map from C2 to C2, which I'll call Chebyshev-like. Okay. There are recursive formulas for these. You can work it out using these expressions for Z1 and Z2. You can do it component by component. So the 0th degree map just sends both components to 3. The first degree is the identity. The second degree, we have to write down what the quadratic expression is. But then after, you can do it recursively. So in this case, I have to give 3 terms, and it's basically because there's 3 terms in each of these. As we go into higher dimensions and other families, this actually gets harder to do. But for this case, it's pretty straightforward to write down. But I'm more concerned with what the dynamics are. All right, if T1 and T2 both are unit complex numbers, so that's one circle and then another circle, right? So you take a circle cross a circle, you get a torus, right? So S1 cross S1. And on that torus, when you take the power maps, you're just multiplying the angles of both of the 2 numbers, T1 and T2, the arguments, multiplying that by a factor of n. So that on that torus, everything is just expanding out. So if you were to look locally, it just looks like you're multiplying by n. Okay. So that's similar to what was happening on the segment that we were folding earlier. Okay. Now, I don't get a torus in C2. I take my my map psi, okay, and see what happens to this torus. And what actually happens is it gets folded on top of itself the way that the unit circle got collapsed 2 to 1 to the segment. I take this torus and it gets folded on top of itself in a 6 to 1 manner because the order of the symmetric group on 3 letters is 6, and the order, whereas before we were looking at the symmetric group on 2 letters, which was only order 2. So that's where the 6 comes from. But anyway, so it folded on, and that looks like a triangle, except it actually turns into a curved triangle, which is this deltoid. Okay, so I'm going to, I think, go ahead and switch back to my whiteboard. Okay, so first of all, with the power map, my torus, you should probably, so you're familiar with taking a square and gluing top to bottom, left to right, you get a torus. If you take a hexagon and glue opposite sides like this, you'll also get a torus that's divided into 6 equilateral triangles. And so that gets mapped down to this deltoid. Each of these individual triangles gets mapped to that deltoid. And in one variable, we had expansion on the unit circle became folding on the segment. Here, expansion on this torus is going to become folding on one of these triangles. So let me explain how that works. So we take this triangle, and if we want to look at just the degree 2 map, we're going to expand by a factor of 2. That actually gives us 4 new triangles. So we'll take this, break it up into these 4 pieces, and each one of these gets folded. So they all get folded on top of each other, stretched out, and mapped to the entire triangle again. Okay, so fold, scale up and then map to the original triangle, and then do that over and over again. Okay, when you're iterating. Okay, the fold points for the folding map on the triangle, if you're just looking at the degree 2 case, you can actually go to a circle inside the deltoid. And this is just for fun. This is, I think, just because I think this is pretty. As you go into higher degrees, so you're folding along more and more lines, which will become curves in this complex picture. And I just think it's pretty to look at what you're folding on. So in the degree 2, this circle gets mapped out to the entire deltoid. Each of these other sort of curvilinear triangle things get mapped to the entire deltoid. And then as you increase, so all of these places are where you're going to be folding over. That's going to go out to the edges of the deltoid. And these just get to be pretty. Okay. All right. I hope that y'all will give me like 4 more minutes because I want to get to the other pretty part. Okay. So just like in the one variable case, we had folding on the segment. Now we have folding on the deltoid. What's happening everywhere else? Everything else goes out to infinity. Okay, just like we did in one variable. Everything that wasn't on the segment went out to infinity. In 2 variables, everything that's not in the deltoid goes out to infinity. Well, what's infinity in this case? We're in 2 dimensions.
In at least 1 coordinate?
Say again?
In at least 1 coordinate?
Yeah, so, well, I mean, infinitely away from the origin, at least.
Okay.
Okay, so they go infinitely away from the origin. But we can actually think about what's happening out at infinity just by imagining that we're standing at the origin and saying, okay, what direction is it going? Okay, you can think of looking at standing at the origin and thinking about what are all the different directions. These are complex directions, right? So it's a little bit funky, but all those directions then give us at infinity another Riemann sphere, which is acting like this, just measuring what the slopes are for these lines going out. Okay, so this is getting into projective geometry, which maybe not everybody is familiar with, but this idea of adding in the slopes for the origin gives us something to study out at infinity. So it's not just a single point anymore, it's this entire sphere. And on that sphere, what we see happening is just a power map again. There's a circle that's mapping around. There's 2 points where things are going, and everything else is either going to one of those 2 points. Okay, so everything that's going out to infinity is either going out to that circle at infinity that's just wrapping around itself over and over again, or it's going to one of these 2 points, which correspond to the 2 axes in C2. Okay, so just to try and get to the last construction here, what we can do is we can look along. We can take sort of slices and say, all right, if I look at a slice, where is a point going? Is it going to that circle, or is it going to one of these other 2 attracting points at infinity? And so what I did when I was first looking at this is I just started drawing pictures using a program called Fractal Stream. So things are either going to the Z1 axis or to the Z2 axis or to a circle that sort of lies between them. And I started getting these pictures. So everything that's blue is going to one axis, everything that's red is going to the other axis. And then here's another picture that is starting in a slightly different place. Okay, so what's going on here? Can we understand these shapes? And that's sort of the last question I want to look at. Let me go and do the last Desmos. Okay, because this is the extra little bit of differential geometry that we get in here. Okay, so here's the deltoid. which is in everything inside here is just folding on itself. And here I'm going to animate just one point moving around the deltoid and the tangent line along that point. Okay, there's a lot of great stuff we can say about this, so I'm going to focus on one particular thing. So if I pick another point, that's the one in orange down here, and I drop a perpendicular from that point to the tangent line. Okay, the place where that perpendicular hits the tangent line is we can call the foot of the perpendicular, just like we do in triangles. Okay, so we have that foot, and as we let the tangent line roll around, that point, that projection, orthogonal projection onto the tangent line moves around, and we get, because of the foot notion, what's called a pedal curve. So this is a pedal curve for the deltoid. Start using this point this arbitrary point that I picked, and as I move that point around, I get different shapes. So if I start right in the middle, I get this three-leafed looking thing. If I move it off to the side, I get this two-leaf looking thing. Move it outside, you get a sort of bean shape. Okay, so we have all these different pedal curves, and this, as it turns out, is exactly what was showing up in my dynamical pictures. Okay, so the theorem is that if you look at the Julia set of these two-dimensional Chebyshev polynomials, okay, so that's where things are acting chaotically. So they're spreading out, or they're going out to the circle at infinity where things are spreading out, and intersect that with a complex line, then you get a pedal curve of the deltoid. Okay, and so what the Julia set is doing is organizing all of these pedal curves into a single object sitting there in C2, and it has this nice dynamical interpretation. Okay, I proved this a few years ago, but the paper where I do that just came out last week, so you can look that up. It's also on the archive if you want, but the published version does have color pictures, which is nice. If you're interested, that actually tells us that we can write down an equation, degree 4 equation. We get this real hypersurface sitting inside of C2 that is the Julia set in this case. And I've gone well over my time, so I will stop there, except to show you these other pretty pictures. So.
Please unmute and join me in thanking Josh. We have a couple of minutes for questions.
So I'm taking trig right now. When will this be like relevant to my life?
So if you're taking trig, then hopefully the cosines and sines felt comfortable. Yeah. So one of the nice things about working with complex numbers is, I mean, everything is nice about working with complex numbers, but they draw all this trigonometry into this really beautiful geometric description. And so when you start, have you worked with complex numbers at all yet?
Yeah.
Yeah. So maybe you've seen something like Dynamical theorem, which says that if you take cosine theta plus I sine theta and raise it to a power, then that just multiplies the angle by the power, right? So we use that a few times.
I didn't know there was a name for that.
Oh, yeah, yeah. I think Dynamical almost wrote it down. Euler actually spelled it out a little bit, but yeah, so there's all these, lots of beautiful connections. So if you like beauty, it's immediately useful to you, and otherwise it's useful for all sorts of things like physics.
I guess my question, I should have been more specific, was like, what class will this be in? Because like I just don't know. There's so much stuff, and it's like I don't know when I'll see this formally, I guess was my question.
Yeah. So you'll see complex numbers pop up at various points if you keep studying math. You'll see it pop up in lots of different classes for describing nice little behaviors.
Not complex numbers, the Chebyshev.
Oh, the Chebyshev polynomials. Chebyshev polynomials. So a bunch of people mentioned like numerical analysis. So numerical analysis is coming up with ways to describe things that are hard to describe more simply. Like, I mean, I guess that might be all of math. So trying to come up with nice approximations. So they would show up in something like a numerical analysis class. My interest in dynamics means that they show up there, but
'Cause I thought dynamics was like an engineering class.
it can be, yeah. So dynamics has several different branches. So it could be used to look at how things push against each other, or how things, basically dynamics just means how does anything change over time. Okay, so if you look at some process and either it's moving continuously with time or it's just sort of happening over and over and over again, what happens in the long term?
So differential equations as well. Sort of like if we write down an equation about how things are changing, these sort of ideas that you shared with us about some things stay the same, some things blow up, some things collapse, some things cycle about. That's sort of like the core of a differential equations class. Different
Also,
objects, but yeah, go ahead.
if I could say, also, some of us are math professors in vastly different areas of math who haven't seen a lot of this. And so we see it by going to cool talks like this and getting interested in it through that. So if you don't run into it in school, you still might run into it in something like this. So thank you, Josh.
Was there a word you were using to describe the orbit that started with an M? Because I had never heard that word before.
Started with a what?
I think it started with an M. Maybe it was something a word you were using, and I didn't want to interrupt to ask. I felt like that was kind of like something everyone should know. So
So I referenced the Mandelbrot set briefly. Is that what you're thinking of?
no, it was like maybe it wasn't an M then. It was like when you were talking about the orientation of orbit or something, you used a word, but I can't remember what it was. Whether it was like less than one or like more than
Is
one.
it the
Modulus?
modulus?
Oh, the
Modulus.
modulus.
Yes.
Yeah. The problem with mathematics being developed by different people is different people come up with different names for the same thing.
Zoe,
and-
Zoe.
Hey,
It's
and-
I can fix it.
and modulus is another word for absolute value in complex numbers. So it just means how far away you are from zero.
Oh.
We're about out of time. Excellent questions. Thank you, Jenna. And so just to wrap us up, a little foreshadowing. Next week, we have a talk from Benjamin Dickman of the Hewitt School. It's going to be talking about enriching divisibility, multiple proofs, and generalizations. Benjamin teaches high school, and so this is going to be a really interesting and accessible one, I think. Okay, thank you. And can you please all join me one more time in thanking Josh for today's session?